Good day, viewers, and welcome to Jalo Science Academy, your best YouTube channel for learning sciences. Of course, I am Mohamed Jalo, your chemistry tutor. I'll be taking you through your chemistry course. Into this tutorial, we are going to look at chemical combination. Of course, we know the smallest piece that still retains the characteristics of an element. We refer to it as an atom. And we're going to look at how these atoms bond with each other to form either molecules or compounds, and how in turn these molecules bond with each other to give rise to giant molecules. Atoms bond with each other by either losing electrons or gaining electrons or sharing electrons. So chemical bonding can be categorized into two. One, we look at the interatomic bonding, which tells us of how bonds takes place between atoms to form either molecules or compounds. In interatomic bonds, there are four types of bonds that we are going to look at under interatomic. So these are the four types of bonds that we have under interatomic bonds. The next we look at is intermolecular, and this one tells us of the force or the attraction that drives molecules to combine with each other. We call it intermolecular bonding. And under intermolecular bonding, we are going to look at two types. One being hydrogen bonding, and the second being van der Waals forces. Or you call them the London dispersion forces. But in this tutorial, I'll be purely referring to them as van der Waals forces. This tutorial is going to be divided into three different lessons. So we start with the first one, interatomic bonding. Of course, the first one we're going to start with under interatomic bonding will be electrovalent or ionic bonds. Electrovalent or ionic bonds, these are bonds that takes place between a metal and a non-metal, okay, wherein the metal is going to donate its valency electrons and the non-metal will accept. As the metal donates, it becomes positively charged. It's going to become a positively charged species. We refer to it as a cation, and the non-metal becomes a negatively charged species. We refer to it as an anion. So the metal is the donor, the non-metal is the acceptor. As the metal donates after losing electron, it becomes positively charged, and the non-metal after accepting electrons becomes negatively charged. Now, these positive and negatively charged species are going to be attracted by a strong force we refer to as an electrostatic force of attraction, or refer to it as a Coulombic force. So an electrostatic force of attraction binds them together as a single unit, giving rise to what we refer to as a crystal, producing a crystal. Okay, so we're going to look at examples of these ionic bonds. The first example we are going to look at is the formation of sodium chloride. In the formation of sodium chloride, you have sodium, which is a solid substance, reacting with chlorine to give us NaCl. Okay, so this is what you have. So this tells us two atoms of sodium combining with one molecule of chlorine to give us two molecules of sodium chloride. But it is only one sodium atom that we're interested over. So we can write the equation like this. Na react with Cl to give us NaCl. Now, sodium is an alkali belonging to group 1 with 11 electrons. And of this 11, you have two core shells and one valency shell with a configuration of 2, 8, 1. And chlorine, a halogen belonging to the group 7 with 7 valency electrons. This is 2, 8, 7. Now, both these species want to be electrically neutral, and they can be electrically neutral by either completing the duplet structure or completing the octet structure. The duplet structure, as in helium, with a maximum of 2 electrons in its valency shell, or they complete the octet structure with a maximum of 8 electrons in the valency shell. So what happens in this situation? This electron that is outside, which is a valency electron of sodium, sodium is going to donate this valency electron here. It donates this valency electron to the chlorine. And when sodium donates, what happens? Sodium now gets configuration of 2, 8. It no longer becomes a sodium atom. It is now a sodium ion. It gets a charge of +1, because when species loses electron, their charges will increase. You see this sodium here with no charge. Okay, and there is also an imbalance in the proton and electron numbers. So the protons have outweighed the number of electrons. That's why you now have a positive charge on the sodium. So the sodium now have attained the configuration of the noble gas neon. And chlorine in turn is going to accept this donated electron. And when this electron is accepted by chlorine, then the configuration of chlorine becomes 2, 8, 8, attaining the configuration of an argon. And the chlorine then becomes negatively charged. So this positive charge and this negative charge are what are attracted by the strong electrostatic force of attraction, or we call it a Coulombic force, that pulls them together, that binds them as a single crystal. That's why you can see sodium chloride, the common salt we use in our various homes, looking like a crystal. Okay, and this is the first example. Another example we can look at is the formation of magnesium chloride. Now, in magnesium chloride, it is magnesium reacting with chlorine to give us MgCl2. So meaning there are two atoms of chlorine that we're going to use. Magnesium is one of the alkaline earth metals in group 2 with configuration 2, 8, 2, having 12 number of electrons, and chlorine a halogen group 7 with configuration 2, 8, 7. So there are 2 atoms of chlorine here. Now magnesium wants to attain neutrality. It wants to be electrically neutral, attaining stability by becoming a noble gas. So what it does, it is going to give away these 2 electrons outside. It's going to donate these 2 electrons to the 2 chlorine atoms that are available. If we look at the configuration using the KLMN shell format from Niels Bohr, this is the nucleus with the protons and the neutrons inside. Okay, so here you have the first shell, which takes up the 2 electrons. So this is going to combine with 2 chlorine atoms . Okay, so these are the 2 atoms of chlorine that are available reacting with this magnesium. So this is chlorine, this is chlorine, and this is magnesium. So when these species react, magnesium being the metal, what happened? One of these electrons is going to be donated to this chlorine atom here, and this other electron donated to this chlorine atom. So when this electron is donated, the configuration of magnesium is now going to change from 2, 8, 2 to 2, 8, attaining the structure of a neon, a noble gas, and thereby getting a charge of +2. Why +2? Because it has donated 2 electrons. Okay, and these chlorine atoms, each of them is going to get a -1 charge because each one is accepting an electron. So this gets -1 charge. And with an electronic configuration of 2, 8, 8, which is an argon. And this charge of -1 is multiplied by 2 because you have 2 atoms of chlorine to give you -2, because the charges has to be equal, okay, for them to be a neutral compound. So this +2 charge and this -2 charge are pulled together by the strong electrostatic force. They are pulled together by the strong electrostatic force of attraction, or the Coulombic force that binds them together. So this is how electrovalent or ionic substances are formed. Now, these substances being formed, there are factors that are responsible. So we're going to look at the factors that leads to the formation of these species. The factors influencing the formation of ionic bonds. One of them we are going to look at is low ionization energy. Low ionization energy being one of the factors. And ionization energy is the minimum amount of energy that is required to pluck an electron from an isolated gaseous atom, or to remove an electron from the valency shell of an isolated gaseous atom. So if that energy is low, then an electron can be easily plucked from that particular species, like in the case of sodium. Removing an electron from sodium becomes much more easier than removing an electron from chlorine. So the ionization energy of sodium is low, whilst the ionization energy of chlorine is high. So in that regard, the electron can be easily removed from sodium and transferred to the chlorine. And similarly, in the formation of magnesium chloride, the electrons can be easily plucked from the magnesium and transferred to the two chlorine atoms to form magnesium chloride, another crystal. The second factor we look at high electron affinity of the nonmetal. When we talk of electron affinity, we're talking of the enthalpy change that occurs, okay? Meaning either the energy that is absorbed or the one evolved when a species gains an electron to become a singly negatively charged anion. So the high electron affinity of the non-metal here, because they want electrons, they are craving for electrons, the non-metals. So they need electrons more than the metals. So in this regard, both of them are participating, wherein this needs more electron than this, then, and this one has lower ionization energy, the electrons can be easily transferred from the sodium to the chlorine, leading to what we refer to as ionic bonds. And the third characteristics we are going to look at here is large electronegativity difference. Electronegativity tells us of the ability of a species to pull shared pairs or bonded pairs of electron in a bond towards itself. If the electronegativity difference between the two species is very high, then the species that is most electronegative have the tendency of accepting the electrons, and the least electronegative species will lose the electron. We saw in the case of sodium chloride, wherein the electronegativity of sodium is extremely low compared to the electronegativity of chlorine, which is high. So in that case, the sodium loses electron to the chlorine atom, giving rise to sodium chloride. So the fourth one we are going to look at is large lattice energy. Now, when we talk of lattice energy in crystalline solids, this tells us of the energy that is released when two ions comes together. So if you have a cation and an anion combining, the energy released is what we refer to as lattice energy. Of course, when a cation and an anion comes closer to each other, they are pulled towards each other by a strong Coulombic force, or we call it an electrostatic force of attraction, which binds them as a single unit. And when these ions combine with each other, high amount of energy is released, and the quantum of energy released also can lead us to having stable compounds form or unstable compounds form. If the energy released is very high, that will lead us to having stable compounds being formed. If the energy released is low, that will lead us to having unstable compounds that are formed. So the quantum of energy released also determines the stability of the product. Because if the total energy released is more than the one that is absorbed, then that will favor the formation of ionic bonds. So next we look at the characteristic properties of ionic compounds. Of the properties of ionic compound, one, they are good conductors of electricity in their aqueous or molten state. Mind you, they only conduct electricity when they are in aqueous or molten state. Reason why they are good conductors of electricity in aqueous or molten state, because in the solid state, when they are solidified, the interionic forces are locked, which prevent the species from moving slowly. So they are not mobile. But when in aqueous or molten state, that interionic force is broken down, releasing the species to be mobile. So you have sodium will break here into sodium ion, Na plus, and the chloride ion. So for this reason, ionic species conduct electricity in aqueous or molten state. Property number 2, they have high melting and boiling point. So the melting and boiling points are high as a result of the strong interionic force. Interionic force, which locks the ion together, giving rise to what we refer to as a crystal. Okay, so as a result of this, their melting point and boiling point can be very high. Because when we talk of melting point, we're talking of the bonds being loosened, and boiling point is breaking down the bonds completely. The third characteristics property is the dissolve in water. The dissolve in water because there is a strong electrostatic force of attraction between the polar molecules and the ionic species. So you have sodium chloride here, Na plus and Cl minus, and then you have water molecule here. So this sodium is attracted to this and is attracted to this. So this strong force binds them together, causing the species to dissolve in water. Okay, so it's as a result of the strong electrostatic force of attraction, which is between this polar substance and these ions. So this force is what allows them to dissolve in water. And property number 4, they are crystalline solids in nature. They occur as crystals. So they occur as solid substances, crystals. Okay, we will have to look at the structure of sodium chloride. That will be in a separate video. We'll look at the lattice structure in sodium. So next, we move over to the other type of interatomic bond, which is the covalent bond. Because when we talk of covalent bond, from the word covalency, it means sharing, and that's mutual sharing. So these are bonds that takes place between non-metals, wherein each of the reactant species contributes an electron to a shared pair. They contribute an electron to a shared pair. And these bondings can either be single, wherein the two reactant species contributes an electron each, or it can be double, wherein the reactant species contributes 2 electrons apiece, or it can be triple, wherein the reactant species contributes 3 electrons each. So we are going to look at some examples of these covalent bonds. And when covalent substances are formed, we refer to them as molecules. They are not ions like we had in the ionic or electrovalent bond. So here, these non-metals bond with each other to produce molecules. First example, let's look at an example wherein we have hydrogen molecule being formed, which is hydrogen gas. Hydrogen molecule is formed when 2 atoms of hydrogen react with each other to give us gaseous hydrogen. And looking at the structure of this, hydrogen, we know in its nucleus has only a proton and in its valency shell having only an electron. So it is going to combine with another hydrogen, only a proton, and then an electron outside here. So when these two species combine, what happens? These electrons are going to be shared mutually because each of them wants to attain the configuration of a noble gas, and that is helium. So get a maximum of 2 electrons completing the duplet structure. So each species contributes an electron to a shared pair. Now makes the total number of electrons in this hydrogen atom here is 2, and the total number of electrons in this other hydrogen atom is 2. So each of them have attained the configuration of a helium. So in this case, if you check this one here, in this case, this is referred to as the bond, and this is the shared pair. This is the shared pair, resulting to what we refer to as a single covalency, because each of the species contributes 1 electron. That's the reason the bond in hydrogen can be represented like this. So we say here hydrogen bonds with another hydrogen to give us this. So this is the bond, and covalent bonds are represented by a dash separating the two species that are being formed. So another example we can also look at is the formation of oxygen molecule. Oxygen molecule is formed by reacting 2 atoms of oxygen to give you oxygen gas. And each of these species contains 8 electrons each, with configuration 2,6 here, 2,6. So if we look at the structure, in the nucleus, oxygen has protons and neutrons. The first shell takes up 2 electrons. The second shell takes 6 electrons. This will combine with another similar oxygen atom. So this atom here want to attain stability by attaining the configuration of a noble gas. Similarly this. So what is going to happen? Neither of them are going to lose electrons. So this is in need of 2 electrons, this in need of 2 electrons. So what happens in that regard? This is going to contribute 2, and this contributes 2, and they bring it to a shared pair. This is how it happens. So in this case, this guy here, it's 2 electrons, and this are 2 electrons. So if we look at this, we have a total of the first shell 2, second shell 2, 4, 6, 8, getting configuration of neon 2,8. In this also 2, 2, 4, 6, 8, 2,8. So both the species have attained the configuration of a noble gas, neon. So these number of electrons here that are shared, we refer to this as the shared pairs. These are the shared pairs. And because each species contributes 2 electrons to the shared pair, we refer to this as a double covalency. And with double covalency, they are represented by two bonds. So we can say oxygen bonds to another oxygen atom to give us oxygen molecules. They are represented by double bonds. These are double bonds, okay? The first bond being a sigma and the other bond being a pi, which we'll discuss in our next lesson. So the third example we can look at, still under covalent bonds, is the formation of nitrogen molecule. So nitrogen molecule with a formula N2 tells us it is two atoms of nitrogen that are combining to give us molecular nitrogen. And each nitrogen atom has 7 electrons. So the configuration is 2,5, 2,5. So if we look at the structure of this, and 5 electrons outside, a lone pair here and 3 unpaired electrons. So also a lone pair and 3 unpaired electrons. So these ones are now going to bond with each other. This has 5 valency electrons. This also 5 valency electrons. This wants to attain the configuration of a noble gas because it wants to become electrically neutral. Similarly, this also wants to attain the configuration of a noble gas. It wants to become electrically neutral. So they are going to contribute 3 electrons apiece. So you have this being formed. Now, if you observe here, you will find out that the configuration of this nitrogen has changed from 2,5 to 2,2468, 2,8. Configuration of a neon. Similarly, this from 2,5 to 2,2468. So each of them attaining the configuration of a neon. So both of them have attained configuration of neon, and you find out that they are shared pairs here. They are shared pairs. And in this case, it is 3 electrons that each of the reactant species contributed to form this bond. So this kind of covalency, this kind of sharing, we refer to it as triple. So this is triple covalency because each of the species contributes 3 electrons apiece. So this is triple covalency, and this is demonstrated by triple bonds. So these are the triple bonds that are formed. The first of them being a sigma and the other 2 being pi bonds. So this is the formation of nitrogen molecule. Of all the examples we've been looking at under covalent compounds has been the same molecules reacting with each other. We are going to deviate a bit from that and look at a situation wherein different molecules react with each other. The fourth example will be formation of carbon dioxide, which is carbon 4 oxide. Also a molecule. Carbon 4 oxide is formed when carbon reacts with oxygen. It gives us CO2. Now, how is this bond formed? In carbon, carbon has 6 electrons, 2 core electrons, and 4 valency electrons. So I'll use red for oxygen atoms. So this is the oxygen atom. This is the carbon dioxide molecule. Oxygen atom, carbon. Now in each of these, oxygen contributes 2 electrons in the formation of this bond here, and carbon also contributed 2 electrons in the formation of the bond. So which indicates a double bond. Here also you have oxygen contributing 2 electrons and carbon contributing 2 electrons given rise, because each bond is represented by 2 electrons. So double bond means 4 electrons. So this is also an example of double covalency. So the formation of carbon 4 oxide or carbon dioxide is an example of double covalency. Next, we look at the formation of water molecules. In water molecule, you have an atom of oxygen combining with 2 atoms of hydrogen. So 2 atoms of hydrogen. This hydrogen has 1 electron, so configuration 1, and the oxygen has 8 electrons, configuration 2,6. So in this case, you have the oxygen atom like this, placed in the center. So the oxygen has 2 lone pairs and 2 unpaired electrons outside. So you have the 2 hydrogen atoms bonding to the oxygen atom. So here, this is the oxygen, this is hydrogen, and this is hydrogen. So this hydrogen contributes 1 electron, oxygen contributes 1 electron, showing us a single bond. Here also, this hydrogen contributes 1, the oxygen contributes 1, showing us a single bond. And there are lone pairs here. So that makes water molecule having this shape, we refer to as a bent shape. We'll discuss the bond angles under hybridization. So this is a lone pair, this is a lone pair, so 2 lone pairs, and you have 2 shared pairs. So this also exhibits single covalency, because you have only an electron being contributed in the formation of the bonds that you have there. So the oxygen contributed 1 electron to form the bond with this hydrogen, also another electron to form the bond with this hydrogen, as you can see them being demonstrated here. Okay, so the next example we'll look at is the formation of ammonia molecule. Ammonia molecule with formula NH3. NH3 tells us we have an atom of nitrogen and 3 atoms of hydrogen. So the nitrogen here has configuration 2,5 and hydrogen 1. So this tells us that nitrogen is going to be the central atom. It has a lone pair and 3 unpaired electrons. And of course, hydrogen has just 1 electron in its shell. This is ammonia molecule being formed. The central atom, nitrogen, with a lone pair, is bonding with hydrogen, and then also bonding with another hydrogen here, and further bonding with another hydrogen. So this is a lone pair, and this is a shared pair. Similarly, this is a shared pair, and this one also a shared pair. So we call them shared pairs. So you have a lone pair and 3 shared pairs. And how did this lone pair come about, which we discussed under the configuration of nitrogen? If you look at nitrogen's configuration, you have 1s, you have 2s, then you have 2p, which has 3 degenerates. So 1, 2, 3, 4, 5, 6, 7. So this here is the core shell, the first 2 electrons, and these are the valency shell. And these are in the same energy level. So this guy will give us the lone pair, and these are the unpaired electrons. So these unpaired electrons, one hydrogen atom will bond here, another hydrogen bond here, another hydrogen bond here. So giving us 1 lone pair and 3 shared pairs. So these are the shared pairs. This is how this ammonia molecule is formed. And lastly, under this, the final example we're going to look at is the formation of methane. Methane, the first member of the alkanes, an organic compound. So the methane molecule has a formula CH4. That tells us we have 1 atom of carbon and 4 atoms of hydrogen. So carbon has 6 electrons with configuration 2, 4, and hydrogen just an electron. So these guys are going to form a bond. Carbon here, this is how it is formed. Let's just look at it and then we can draw the diagram easily. Carbon's configuration. Carbon, of course, has configuration of 1s2, 2s2, and 2p2. So let's look at this. One, 2, 3, 4, 5, 6. This is following the rules for filling orbitals of Bau-Paulian horns. But looking at this configuration, this is the ground state configuration of carbon. Ground state configuration. So this one is going to be energized so that the electrons become excited. And if it is energized, one of the electrons become excited, this electron in the 2s orbital will move into the 2p orbital. So you have the configuration looking like this. So you now have it to be 1, 2. Instead of 2 electrons here, you have only 1. You have 1 here, and one of these electrons now moves to this point. So given space for 4 hydrogen atoms to be bonded, refer to this as an sp3 hybridization. Okay, so here, one of the hydrogen atoms will bond here, the other hydrogen atom bond here, the other bond here, and the other bond here. So we can demonstrate this using the diagram. So in this situation, so you have this to be the methane molecule. So you have carbon forming a bond with hydrogen here, forming a bond with hydrogen here, forming a bond with hydrogen here, and forming a bond with hydrogen here. Though this is not the correct structure because it looks like this, you have carbon bonding with hydrogen here, bonding with hydrogen, you have here, and the other one being a wedge, okay? The other hydrogen, meaning it goes inside, giving us a shape referred to as a tetrahedral molecule, but that will be discussed under hybridization. So this is how the methane molecule is formed. So next we look at the Lewis dot structures. These diagrams that we've drawn, we can simplify them using the concept of Lewis dot structures.